Yeah, let's welcome next speaker, Sourav Sarkar from SN Bose National Center for Basic Sciences, with the topic of geometry-mediated interconvertibility between spin glass and superparamagnetic relaxation in spinel ferrite nanostructures. Thank you.
Hi everyone. So yeah, I think I'm audible. So first of all, for better visibility, better communication, I'm turning off my video. So yeah, thank all the organizers for giving me this chance to be a part of this grand event. So I think this is one. I think this is very unique of its kind. This 24-hour, I think non-stop conference. This is actually, it's a great opportunity for me. Really grateful. It's a great pleasure for me. So today today. Sorry, I think. Excuse me, just my slide, I think. Okay. Yeah, now it is. Yeah. So today I'm going to talk about geometry mediated interconvertibility between spin glass and superparamagnetic relaxation in spinel ferrite nanostructures. So I am Sourav Sarkar. I'm doing PhD in SN Bose National Center for Basic Sciences, Kolkata, India. So this is the basic outline of my talk. I have a motivation, then synthesis, and then I'll go with the flow. So the motivation. So there are a lot of research which says that the spinel ferrite system, they show spin glass nature in different kind of spinel ferrite system. On the other hand, we also have different kind of research which shows that the same spinel ferrite system also shows superparamagnetic nature for the same system, sometimes for the different systems. So with this scenario, these two almost different scenario in the same system, let us pose this question: that what is actually happening? Can the two behaviors be tuned by geometry engineering in the same system? That was our main motivation with that. So before going into the details, I just let me just recapitulate what is a spin glass. So spin glass systems are mostly broadly they are characterized by random yet cooperative freezing of spins. They are actually the one key ingredient for spin glass is frustration. On the other hand, superparamagnets are collection of magnetic nanostructures. They randomly flip direction, and they are characterized mostly by the broad distribution of relaxation times due to anisotropy, and also they show slow dynamics. So with this thing in hand, we have also chosen the same spinel ferrite system, which is a rich playground where we can play with the cationic disorder, where we can dope one thing and in the tetrahedral site or in the octahedral sites. And out of the spinel ferrite, we have chosen zinc ferrite in two different geometries because of non-magnetic zinc and magnetic iron, because then the magnetic disorder can also be induced. So for that, in the zinc ferrite system, we have chosen two different geometry. One is nanoparticle, another is nanoholosphere geometry. That I'll come later. So this is the synthesis and characterization slide. We have synthesized our sample in solvothermal synthesis with olalamine as the surface modifier. Now this is the XRD pattern with the Rietveld refinement analysis. You can see that both the systems are actually showing this. The chemical formula can be can show that both the non-magnetic zinc and the magnetic iron is both at the tetrahedral A site and at the octahedral B site. So both the systems are synthesized in mixed spinel form. Next, this is the TEM image for my systems. This is for nanoparticle and this is for nanoholosphere. So you can see this is the particle, they are compact in nature. On the other hand, the nanoholosphere, they have a hollow core inside and there is a thick shell around there. So the nanoparticle diameter, they are around 49 or let's say around 50 nanometer. On the other hand, the holospheres, they are actually 170 nanometer in diameter, and the thickness is around 50 to 60 nanometer for holospheres. So with this visualization of my sample, I move on to the DC magnetic properties of my sample. This is for the nanoparticle. This is for nanoholospheres. This is the blue one is the zero field cool magnetization curve, and the red one is the field cool magnetization curve. So with that, we can see that from 2 to 150 Kelvin temperature, and there are a lot of peaks are there, making their origin hard to distinguish. So for that, we have also carried out the magnetic image curve measure. We have also plotted the image curve. With that, the image curve are fitted with the law of approach to saturation for both the system. This is for particle, this is for holosphere. Now we can see that we have from the fitting, we have actually 3 times higher anisotropy in nanoparticle than in nanoholosphere. So this is the first indication that if we have a higher anisotropy, then maybe there is an indication that we can have a broad distribution of relaxation time that can lead to superparamagnetic nature. Now, not gaining much information from the DC magnetic properties, we have also shown the AC magnetic susceptibility for our system. Now, this is the real part of AC susceptibility, and this is the imaginary part. This is for nanoparticle, and this is for nanoholosphere. Now, you can see that from the real part is also not very different for the two systems. On the other hand, if we zoom into the imaginary part, that is chi double prime, then something interesting happens. We can see that we are actually getting 2 peaks. The 2 spin freezing temperatures are there, one around 25 Kelvin temperature, and another is around 35 Kelvin temperature. Now with this, we can see that there is a shift in the peak temperature with the frequency of the AC magnetic field with different frequency. Now this is a signature. This is a fingerprint of spin glass nature, or let's say the superparamagnetic nature. Now, to identify exactly the peak position, we have fitted each plot with bi-Gaussian fits. With the fits, we have actually identified the peak positions. Now, once we have the peak position, we can estimate the Meadows parameter from them. So now this Meadows parameter is actually 0.3 for nanoparticle for the lower temperature curve. On the other hand, the same Meadows parameters is around 0.08 for nanoholosphere for the higher temperature curve. Now, this is a second indication that the nanoparticles are dominantly can be of superparamagnetic nature. On the other hand, the nanoholospheres can be of spin glass nature. So, but this is also not a conclusive evidence. Now we further proceed to the other analysis of the temperature that we have achieved from the bi-Gaussian fit. We have fitted it with the Arrhenius law. Then we have fitted it with the power law, and also taking that value of tau prime from the power law, we have also fitted it with Vogel-Falcher law. Also, we have fitted with the Vogel-Falcher law independently. All of the analysis shows that there can be a dominance of superparamagnetic nature in nanoparticle. On the other hand, nanoholospheres, they show a relaxation time of typical spin glass. Now, these are all not very conclusive evidence. So, in search of a conclusive evidence, we have next done the wait time dependent relaxation, but they are also giving the same information for both the system. We have also fitted it with stretch exponential. I'm not going into the details. On the other hand, we have also checked the memory effect using the wait time dependent relaxation. There also we are getting almost the same information. Not very much difference is there. With this thing, we proceed to have the field cool memory effect. Now, this is kind of a conclusive evidence. So in the field cool memory, first of all, we record the field cool magnetization curve. This is called the FC reference curve, marked in green. Then after coming to 100 Kelvin, we cool down the system to 5 Kelvin with the application of 100% magnetic field with intermittent halts at 80 Kelvin, 60, 40, and 20 Kelvin. During each halt, we switched off the magnetic field and allowed the system to relax for around 1 hour. After coming to 5 Kelvin, we now, in the presence of the same 100% magnetic field, we now measure the magnetic moment in the heating cycle. If the system, that is the red curve, this is the memory curve, if the system can retain its memory, then it should follow the cooling curve, that is the blue curve. Now you can see for the nanoparticle, it is not very, it is not for, I mean, the red curve cannot follow the blue curve very much well, but in the hollow sphere you can see that the following is much better. Also, I have plotted the derivative curve. You can see that for nano hollow sphere, the four peaks, the four memory peaks are there for nano hollow sphere. On the other hand, only two memory peaks are there at 20 and 40 Kelvin for nanoparticle. So a more prominent FC memory effect is there in nano hollow sphere. On the other hand, the more conclusive measurement is a zero field cool memory. Now, the zero field cool memory is we first, the green curve is a zero field cool reference curve. On the other hand, after going to 100 Kelvin temperature, we now cool down the system without the application of any magnetic field, that is zero field cool. Without the application of any magnetic field, we go down to 2 Kelvin. Now here, while going down to 2 Kelvin, we actually also applied two intermittent halts, one at 80 Kelvin, another at 20 Kelvin. During the each halt, we also this time also allowed the system to relax for around 1 hour, and then we measured the system, we measured the magnetization of the system in the heating cycle. This is the blue curve, this is the memory curve. Now if we take the difference of those ZFC reference and ZFC memory curve, we get the red curve. This is the difference curve. Now if the difference curve shows the dip at those temperatures where the sample was allowed to relax, then we can say that okay, the system exists zero field cool memory. Now we can see that for the nanoparticle, we have only very weak memory deep at 20 Kelvin. On the other hand, for the hollow sphere, we are actually having a strong memory deep at 20 Kelvin and 80 Kelvin, around 80 Kelvin. So these actually tells us conclusively that there is a superparamagnetic dominance in nanoparticle. On the other hand, for the nano hollow sphere, the behavior is more to spin cluster glass. Now, why this cluster glass is happening? Why this behavior is happening? So to solve, I mean, to solve this issue, we are actually we actually shown the one excerpt of the famous phenomenal paper by J.M. Meadows, that to have a spin glass, we have to have frustration along with disorder. Now, this is our nano hollow sphere system. Now, if we can simulate the nano hollow sphere system, we can see that while during synthesis, while cooling down to the room temperature, there is an internal stress developed in the system, which is directed towards the center of the hollow sphere. Now, for this, we can invoke the notion of magnetostriction. Now, what happens is that there is internal stress generated in the system. Now, this internal stress is denoted by sigma, and this is the lambda zero. This is the coefficient of magnetostriction. Now, the same thing can happen for positive magnetostriction sample and negative magnetostriction sample. What is happening is actually for positive magnetostriction sample, lambda zero is positive. For magnetostriction energy to be minimum, we have to have phi either zero. This is the angle between the direction of stress and the direction of magnetization. This phi should be either 0 or 180. So for that, the magnetization direction can be along that can be along the direction of stress or along the direction opposite to the direction of the stress. So the intermediate layer between two oppositely oriented layers can have frustration. So the spins there do not know which way to align. The same thing can happen for a negative magnetostrict sample. Here, phi should be pi by 2. So the moment can orient themselves either clockwise or anti-clockwise. So again, the intermediate layer can have frustration. So with this interpretation, I conclude my work that more prominent FC and ZFC memory is there in nano hollow sphere, that in case of nanoparticle, we can induce frustration just by restructuring the morphology. And the most important conclusion is that we can have different spin relaxation behavior in the same system just by restructuring the morphology at the nanometer scale. This is the most important conclusion of my work. The work is already published. So I'd like to acknowledge my funding agency, my supervisor, my teammates. Yeah. So thank you. This is all. And any questions?
Thank you, Saurav. Nice talk. So we have time for only one question. Is there
Yeah,
any
sure.
questions?
Yeah, please.
So I have one question in your
Please.
zero field memory.
Yeah.
So how do you control the super paramagnetic effect?
How do I control the superparamagnetic effect? Sorry.
So in here, you just
Uh-huh.
said that the effect is due to paramagnetic,
Okay. Yeah.
I mean nanoparticles, right? So
Nanoparticles. Yeah.
so how do you control this?
How can I control the size of the nanoparticle, or
It's
uh,
in general the difference between the first figure and the second figure.
okay, okay. So yeah. So let me tell you this. That this. I mean, there are several. I mean, not much, but there are papers that if your system shows the zero field cool memory, then only it is a superparamagnetic. I mean, then only it is a spin glass relaxation. On the other hand, if your system is a superparamagnetic system, then it cannot show zero field cool memory. I mean, in the earlier around 2000, people are actually confused that how can we distinguish between superparamagnet and spin glass, because both of them show different slow spin dynamics. But this is the zero field cool memory effect is the one that actually conclusively say that the presence of zero field cool memory actually indicating that there is a spin glass nature. On the other hand, absence of that can actually indicate superparamagnetic nature. So there are a lot of theory papers are also there. I can control that. Okay, I have measured it for the nanoparticle, that if any superparamagnetic nature is there, I have shown that okay, very weak zero field cool memory is there. Uh, Very weak. On the other hand, very strong zero field cool memory is there for nanoholosphere. So in every talk I have already I have been consistent. I guess I believe that there is a dominance of superparamagnetic nature in nanoparticle, because we are actually experimentally. So we cannot say that there is no superparamagnetic nature in the nanoholosphere also, but we can say that the superparamagnetic nature in dominant in nanoparticle. On the other hand, the spin cluster glass nature is dominant in nanoholosphere. Also, another thing is the magnitude of the field cool memory, because this magnitude is also a significant indicator that your system is superparamagnet or let's say spin glass. I think that answer your question. I hope.
Okay, thank you.